Hello everyone and welcome to today's webinar, The Evolution of Precision Laser Alignment, brought to you by CBM Connect. I'm Nick Rush, the Media Specialist of Mobius Connect, and I'll be your moderator for this session. First, I'd like to introduce today's presenter, Terry Southall from Hamar Laser Instruments. Terry, how are you today?
I'm doing good today. How are you, Nick?
Doing great, thank you. Before we get started, I'd like to review some important information with our audience. This webinar is being recorded and you'll be emailed a link with access to the on-demand version of this webinar tomorrow. The recording of it will also be shared on CBM Connect. Mobius Institute is a worldwide provider of reliability improvement and condition monitoring education dedicated to supporting plants and helping them become safer and more successful. Mobius Institute's key advantage is its unique training style that features innovative 3D animations and software simulations, making complex topics easier to understand. The Mobius Institute Board of Certification is an ISO accredited certification body that provides globally recognized certification to CBM practitioners and reliability professionals at any stage in their careers. To view our global training schedule, please visit mobiusinstitute.com. The Mobius Connect community is about you, providing you with the space and technology to connect with the right people and resources to help you solve problems, continue learning, and share your experience too. Once you've created your free profile, start connecting with other industry professionals wherever you are in the world in any language. You can also continue your educational journey live with the Connect conferences or online with the Connect knowledge base. Or you can become a member of your regional Community Connect group to gain access to additional resources and attend live or virtual meetups with professionals from your area. Get started by creating your profile and joining the community at mobiusconnect.com. Today's webinar is produced by CBM Connect, the leading online educational community, which is published by thought leaders and experienced industry professionals from all over the world. CBM Connect allows you to organize content based on your areas of interest. You can get started on CBM Connect by creating your profile on Mobius Connect and selecting which technologies you'd like to stay up to date with. You can visit cbmconnect.com directly to access hundreds of on-demand webinars, interviews, videos, white papers, and more. Furthermore, if you're interested in contributing to the CBM Connect knowledge base, please reach out to us during the webinar through the question panel, and we will be happy to share more information with you. Now, once again, for those of you just joining us, welcome to the Evolution of Precision Laser Alignment. If anyone has any questions through the webinar, go ahead and type them in the question panel of your GoToWebinar screen. And at the end of today's session, Terry will be more than happy to answer some of the questions. Now, your questions will be answered on the air anonymously, and if we run out of time and don't get to the question, Terry will reach out to you directly after the webinar to make sure that all of your questions are answered. All right, Terry, I'm going to go ahead and pass the presentation over to you now.
Okay, well, we'll get started. Hello, everyone. I'm Terry Southall from Hamar Laser Instruments, and today's discussion is going to be around the evolution of precision laser alignment. Now, I'm going to touch on at a high level some of that evolution, but we're going to primarily talk about geometric laser alignment, and we're going to talk about shaft laser alignment in this webinar today. Let me fix that. In today's discussion, I'm going to do a quick introduction of myself to introduce who I am for those that do not know me. We're going to talk about the laser origins, where it started, and where it currently is. We're also going to do a laser alignment timeline within industry. We're going to talk about geometric firsts, and we're going to talk about shaft alignment firsts. We're going to talk about the best kept secret, and I'll bring that up when it arrives. We're going to discuss today's industry and what the expectations are, and then we'll have some thoughts and takeaways. First is the introduction. So normally when you introduce the company. The company is going to be a little bit later on in this webinar, so I want to introduce myself first. I'm Terry Southall. I was born and raised in the Florida Panhandle. I served my country in the United States Air Force for 15 years. When I got out of the Air Force, I got into manufacturing in a aerospace turbine motor division facility, and then I moved into wood products based around oriented strand board. If you don't know what oriented strand board is, that is your 7/16 panels on your roof, or the tongue and groove panels that you walk on if you have a crawl space. After that, I moved on into the business sector, and I became the strategic account manager for a reliability training company out of Florida. And I spent a little bit of time with a consulting firm also out of Florida as the business development manager. I'm currently the global brand and distribution manager for Hamar Laser Instruments. I am a family man, happily married. I have 4 adult children and 1 grandson who is my world. I do have education. I have 3 associate's degrees, 1 bachelor's in management, and I have a master's in adult education and training. But you aren't here to listen to about me. So let's talk about laser origins. Where did the laser come from, and who were the developers originally to be able to present what we currently know as spot beam, fan laser, single beam systems, point and shoot, or auto scanning lasers that we currently have in industry today. So the laser is a device that emits light through optical amplification. So there's radiation that's involved within this amplification. So it's electromagnetic. If you did not know, laser is an acronym. It stands for light amplification by stimulated emission of radiation. The question I initially asked was who invented the laser, and it took me down a lot of rabbit holes when I went out into the IoT to looking for who actually developed the laser and who is accredited for the laser. So we do know that Albert Einstein in 1970 presented the theory of a laser system, but he did not have time to perfect it, nor did he have a group of engineers with him to do that. What happened was in 1953, a group of engineers at Columbia University did invent, the first one was called the microwave amplification by stimulated emission of radiation, or MASER. So it was a microwave amplification instead of a light amplification. The problem was due to the wattage of the MASER, they could not get a distance that was adequate enough to make it sustainable. So in 1958, the same group of engineers invented the laser. You can go into many websites to view the theory behind it and who is accredited for it. There are 3 engineers that were part of that group of engineers out of Columbia that take claim for it. The very first operational laser was designed and produced by Theodore Maiman. He made the first laser in May of 1960 in the Hughes Research Laboratory in California. What he did was he used, and you can see the image to the right, he used a high-powered lamp, almost like a hydrogen or halogen lamp, and then he pushed it into a synthetic ruby that was coated, where the case was coated in silver to be able to get a beam. Today's lasers are mostly classified as Class 1 or Class 2. Class 1 system is like your CD-ROM or your laser printer. Class 2 is going to be what we're going to talk about today, which is your laser alignment system. So now that we know where the laser came from, let's talk about a quick timeline of the first that have happened within precision laser alignment. One of the first things I asked as well was who invented the first laser alignment system. As you can see in the top left picture, that is the Perkin-Elmer helium neon, or HENI, laser that was produced in 1965. So a Cornell educated engineer is accredited for inventing the first laser. So almost 60 years ago, while working at Perkin-Elmer. He then founded his own company in 1967 to further develop the system. His goal was to create a laser system that would solve problems ranging from simple geometric alignments to multi-axis complex alignments. A lot of people do not know who that person is, but that person is Martin Hamar, the founder and owner of Hamar Laser Instruments. Here's some milestones that pick up when Martin actually opened up his company in 1967, and we'll go through a couple here on showing you what the firsts were. The initial picture that you saw to start this presentation was the model L400. It was a straight line alignment laser. Martin had to create a stability mount for that laser in order to sit it on and be able to operate it and get the readings that were required by the facilities that were purchasing it. This was the start of many patents that Hamar Laser currently has centered around precision alignment. In 1976, Hamar Laser introduced the model L711. This is the first auto-scanning laser plane that was developed in industry. The problem is it turned at 300 RPM, so Hamar Laser also had to develop a target that was able to capture that laser beam during that rotation. Yet another patent that was eventually collected by Hamar Laser. To give you an understanding, so I'm going to shift over to shaft alignment. In 1981, a company out of Germany called Proof Technique introduced their first shaft alignment system called the AL2000. The AL2000 was not a laser system. It actually had dial indicators and a computer that you actually entered all your data in, and then you used the crossover dials to be able to align the system. In 1981, Hamar Laser introduced their L800 spindle laser alignment system. This was the first alignment system to feature an invisible infrared diode-based laser. So before that, they were using Heine lasers quite a bit. This is the transition into a diode-based laser, and at this time, it was invisible, so you could not see it. You had to have a sensor to be able to read it on the other end. 3 years later, in 1984, Proof Technique introduced their Optaline system, and it was called the Optaline IR. It updated the ALI 2000. It was the first laser shaft alignment system available to the public, and it also provided an invisible diode-based laser. In 1984, another company started, Fixture Technic, who would later become Fixture Laser. A company out of Sweden was tasked to do laser-based measurement systems for the companies that they were building fixtures for, and they created their first helium neon cathode or helium neon filled cathode tube laser light system, and ironically they called it the Fixture Laser system. In 1989, now Fixture Laser, they introduced the Combi Laser. It was the first shaft alignment tool to have software installed that carried out all the calculations. So they introduced the first system or application that you would be able to enter in all your data in or receive the data as it was collected. In 1990, Hamar Laser introduced their first shaft alignment system called the S640 Coupling 2. It featured the first advanced visible diode-based shaft alignment system, and it was the first 4-axis system on the market. So this is a transition in 1990, and this transition followed with all of the other laser companies. Everybody started going to the visible laser, including Proof Technique, who introduced a year later their Optaline V, V standing for visible. So they were able to have their visible diode-based laser. It was considered the Optaline IR on steroids. It was a lot faster, a lot quicker. 2 years later, another company got introduced into the market, Damalini, who would become Easy Laser, introduced their first shaft alignment system called the Damalini 505. It laid the foundation for the Easy Laser series of alignment tools that you see today. 3 years later, Fixture Laser introduced their Shaft 100, which would replace the combo laser with updated technology, including a touchscreen, which very few laser systems had, and an updated user interface. The last milestone I'm going to go into directly is in 2000, Hamar Laser introduced the S650. This was the first wireless shaft alignment system to hit the market. So before that, all alignment systems had to have a wire connected to both to the target going to the computer to be able to collect data. So this was the first system to provide that wireless information directly to the computer. It's also the first time that Hamar Laser introduced the dual beam unidirectional technology. That's two beams going in one direction. Now, if we want to look at it starting in 2000, we can look at what transpired within laser alignment since then. So the introduction of 3D laser alignment systems, and everyone by 2006 was using wireless technology in their laser alignment systems. In the 2010s, the precision for misalignment got smaller, so the number of zeros after the dot for inches or for millimeters got greater and greater as the system became more in tune with identifying misalignment or offset within that system or any system. Automation features were prevalent, reducing human error. So introduction to the laser systems and what they are today reduce a lot of that human error within the facilities. In the 2020s, laser alignment systems began integrating the Internet of Things, the IoT, and predictive maintenance platforms. They also introduced continuous monitoring for machinery alignment and predictive maintenance strategies to prevent downtime and extend equipment lifespan. So what's in the future for laser alignment when we look at a timeline? Well, obviously, artificial intelligence is being looked at heavily. Artificial intelligence will be able to provide you feedback or algorithms to be able to assist you better. I don't think we're at that stage where a robot is going to perform the alignment, whether it's at a machine tooling facility or out in a gas or oil field or inside a paper plant. So the idea here is it's more integration and learning algorithms for the laser alignment systems. And all in the automatic diagnosing alignment issues and suggesting corrective actions, that is currently being looked at now. So it's present instead of future. So that's a quick timeline just to bring you up to speed on a few of the systems that are out there or were out there to be able to bring the systems that we currently use in today's market. Next, I want to talk about the best kept secret. And a lot of people ask me that, what is the best kept secret? Well, when it comes to laser alignment, whether it's geometric or shaft alignment, the best kept secret in industry right now is Hamar Laser. Company started in 1967. It's a family and veteran owned and operated. It's the only made in America laser alignment company currently in existence. They have 25 patents in both US and Europe, and they're currently working on 2 patent pendings. They do a lot of built to suit and custom made designs for niche markets. And I'll give you an example for niche markets. If you're flying in an airplane in the next month, one of those niche markets is the adaptation of aligning the wing to the fuselage of an airplane. Hamar Laser developed a system to allow that wing to stay within that degree of relativity going into the fuselage, so no cracks or any imperfections would happen during the installation of that wing. So if you didn't know, Hamar Laser is embedded in a lot of those type of companies where you're not going to see the Hamar name, but you're going to appreciate what they do for the end product. We have global regional managers and distributors currently in 72 countries. We provide both geometric and shaft precision laser alignment systems. We are a solely laser alignment company. That's the only thing that we make. We introduced 5 new systems in the past 4 years to hit the market. We're headquartered out of Danbury, Connecticut. We do extensive research and design that goes into each system that is created. And speaking with everybody that's probably never heard of Hamar Laser, that would make us the best kept secret in reliability and maintenance. One of the sayings that we had in the 1970s and 80s is you need a Hamar for that. So you'll definitely need a Hamar for that. So going a little bit more into what Hamar Laser does and where they're at. So where can you find a Hamar Laser system? So the first alignment system was used in industry was a roll grinding machine at a paper facility. That was the very first application that was used with the L400 back in 1968. In today's industry, we're in aerospace, shipbuilding, automotive, power generation, wood products, the military, chemical, pharmaceutical, just to name a few. But we're also working directly with contractors and service companies in every market as well. Since we are strictly a precision laser alignment company, here's the list of all the systems that we offer. Keep in mind, some of these systems may have subsystems within them. So both for the geometric and for the shaft alignment system, we created a system for a specific need, and then we have alternate applications or alternate accessories to be able to make it a one-off or a single fit for a specific requirement. As you can see in the pictures, some of the examples of what those are. Now, since we are strictly precision laser alignment, one of the things we do is we look at technology and what we can do to improve our systems. And I'm going to give you 2 examples in the difference in technologies that's out there. First one I'm going to talk about is auto scanning versus point to shoot or point and shoot lasers. When it comes to geometric laser alignment, there are two types. Auto scanning, that laser will spin at 360 degrees, either in the x-axis, the y-axis, or the z-axis. And depending on how the system is, you're able to get more than one reading using targets. So you can place targets wherever you want, and that laser will auto spin. So you don't have to have more than one person to be able to apply that application. The point to shoot laser, that's literally having two lasers that have to meet each other, and you have to point them regardless of the distance that you've created. So it takes a lot more time to be able to set up a point and shoot laser to be able to check for flatness, straightness, squareness, those type of applications. When it comes to shaft alignment, there are two types of shaft alignment systems out there. There's single and dual beam technology, and there's crossover technology. So with dual or single beam technology, that is one or two lasers going in one direction and going into a target at the other end. For crossover lasers, that's two lasers going in opposite directions going into a target on the end of it, on the separate, or going into a sensor on the separate target. So it's having to go across each other. So what's the difference between the technology? Well, with two beams or one beam going in one direction, you do not have to do what's called a rough alignment, a pre-alignment before you actually put the lasers on, because you're not having to align the lasers to see the sensor. The sensor is automatically pointed, the laser is automatically pointed at the sensor. So this removes the part of that pre-alignment check. Now, I know what everybody's going to say here. Well, everybody does it naturally anyway. So as a millwright mechanic taught to do an alignment, the first thing you're taught is grab your straight edge and check and make sure you have a good rough alignment on that system before putting the laser on. What we're saying is, why would you buy a laser to physically do a rough alignment when you can let the laser do that for you? When it comes to two beams, two directions, or the crossover lasers, it often requires a rough in even during the sweep. So when you sweep the lasers around the shaft, depending on your offset and angularity, the laser and the target going in both directions can lose connectivity and you have to realign. So with the two beam, one direction that Hamar Laser has, we're negating that need to be able to have another rough alignment while you're rotating the lasers around the shaft. Let's talk a little bit about today's industry. So in today's industry, it's all about getting as close to zero as we possibly can, and what is the value of that zero. So when we ask what is the value, when we ask what is the value, almost everything in today's industry comes with a value. There's cost. So whether it's maintenance cost or operational costs or storeroom costs, there's always a cost value placed in there. When it comes to revenue, what about production revenue? What about sell revenue or the product revenue that we make? When we get a little bit more finite, when we talk about value, when it comes to maintenance, we can talk about mean time between failure. What happened to that machine through a trended amount of time? Some companies also go as far as mean time between repair. So mean time between failure means there was a failure point of that system, and that's all we know about it. When we do mean time between repair, we can know that when a human touched that system and for how long it ran before it had to be touched again. When we talk about precision laser alignment, we talk about accuracy and precision. So how do we measure accuracy? Accuracy is the degree to which a measured or calculated value is close to the actual value. So when we're trying to align anything for precision, we're trying to get to as close to zero as we possibly can. In today's industry, accuracy is measured by something. So in imperial measurements, it's thousandths of an inch or mils, and I'll talk about those two in just a second. And in metric, it's talked about in millimeters and microns. But there's also another option for measurements of laser alignment, and that is degrees. So if they're measuring in degrees, we measure arc seconds and arc minutes. So what does that mean for accuracy? Well, what are we trying to do? We're trying to make something level, trying to make something square, something flat, something straight, something parallel, something perpendicular. So we're trying to improve the system as we go, to get as close to zero as we possibly can. Now, let's look at the different measurements that you can actually have depending on where you are in the world. When it comes to imperial measurement, you have thousandths of an inch in mils. So thousandth of an inch is 0.001 inches. That's what a thousandth of an inch is. So if you have a sheet of paper on your desk right now or right in front of you, if you look at that sheet of paper, that thickness of that paper is about 0.02 of an inch. When it comes to maintenance and expectation of alignment, inside a 1-inch deep groove rolling elements, spherical rolling element, is what's called an I'm going to have to say this is a hard one for me, elasto hydrodynamic lubrication, also known as EL film, between the rolling element and the outer race of a 1-inch or a 25 millimeter bore deep groove ball bearing. Well, that's also 0.02 of an inch. So if you've ever wondered why industry says when we're dealing with something larger than a 1-inch shaft, we want to keep it within 0.02 at the far bearing, that's your explanation right there, because we have 0.02 of clearance to play with before metal touches metal. Majority of your shim sizes in the United States and those that use imperial measurement, the shim sizes are going to be measured in thousandths. So somebody got smart. Somebody said, wait a minute, why do I want to say 0.001? That's a fraction. So why can't we change it to something else? So what we changed it to was a mil. So a mil, 1 mil is equal to 1,000th. So if we say 5 mils, that's 0.005 thousandths, or 0.005 inches, or 5 thousandths. It comes from the Latin word millissimus or milli, which both stand for thousandth. It's mainly used in the United States to turn fractions into whole numbers, so that way we can physically say a whole number instead of a fraction. It's a lot easier to say. So when we change 1 mil or 1,000th of an inch to millimeter, there still has to be a change within that fraction to be able to show that. Now over on the metric side, we have millimeter or we have microns. What is a millimeter? A millimeter is 1,000th of a meter. It's also referred to as milli as well. All bearings used in industry, and this one kills me, and I love talking about it. So all bearings we use in industry are in millimeters, but all shafts that we use in the United States are inches. So when I have a 1-inch shaft, I need a 25 millimeter inside diameter bearing. So, and it still even gets more finite than that. It's technically not even 1 inch. It's 0.9864, 9867. So it gets even smaller as we go in. So even though we still use inches, we also use millimeters within industry, especially around imperial measurements. You can also figure out how many mils convert into millimeters by dividing whatever that mil number is by 39.37. So it's a simple way to remember. If I want to find out how many millimeters 1 or 5 mils is, I can just divide that 5 by 39.37. For those that already did that, you should have gotten 0.127 millimeters. So 127, what we're about to talk about now in just a second, microns. So what is a micron? A micron is 1/1,000,000th of a meter. It also has its own symbol, and I call it just the crazy U. 1 micron is 1 to 25 thousandths of an inch, or 0.0000394 inches. So it's quite a bit of finite when it comes to an actual inch. So when we talk about microns, one of the things that I always ask is how many microns can you physically see? Well, there's a wide range of people on the internet that say you can see down to 25 microns, but there's a wide range that say you can only see up to 70 microns. So right now the average at what everybody's saying is 40 to 50 microns, and I'm going to stick with that in industry. So to give you examples of what a micron is, a grain of a coffee ground is 300 microns, or a piece of table salt is 100 microns. Your human hair, it varies, but it averages around 70 microns. If you were to take a pen and actually just sit there and put a dot on your paper, that averages about 60 microns. And that EL film that we talked about over in thousandths of an inch, it is 50 microns of clearance. So when I say microns, if we can't see anything lower than 40 microns and we're using a hammer and cold chisel to take off a lock nut on a bearing, as soon as I hit that chisel, if any metal smaller than 40 microns jumps into the bearing, am I going to see it? And so that is the understanding. We cannot see smaller than, I'm going to say it, 40 microns. We have a clearance of 50 microns between the rolling element and the outer race of that bearing. The other part is measured in angles, and I'm just going to talk about arc seconds. An arc second is 1/3600th of 1 degree. What does that mean? It's used to measure small angles such as distance between two objects. And high accuracy machinist bubble level is typically 4.15 arc seconds. And you can easily calculate what the arc seconds are as long as you know what the radius of that circle is and the angle that it moves. So I gave an example there of 2 millimeters on a 100 millimeter diameter circle, which is 50 millimeters radius. So it gives you the calculation. So it moved 82 arc seconds. Now, when we get to arc minutes, that's just a lot bigger than an arc second. So that's more used in astrology and astronomy. So it's measuring something bigger than what we need to measure in a facility, since 1 degree is 1/60th for an arc minute. So it's a lot bigger. Prime example I showed there was if you're on the equator and you're looking at a full moon, it's going to read across that full moon 31 arc minutes. So how finite is measurement these days? And that's one of the questions that I asked when I started this. How low can our measurements go currently, and what are we looking for? So I'm going to use two examples of the Hamar laser systems that we currently have on the market: the L743 triple scan geometric laser and the X885 axis shaft alignment laser. So when you look at the measurements of what they do, for the triple scan laser, it is spinning, so it's an auto scan laser, and those targets are picking up the data from distances. So you still buck in, you still have to be able to do either a 2-point buck in or a 3-point buck in to be able to get zero and have everything slated on a level plane before you start. But it allows you to do that with that auto scanning due to the fact that that laser can just sit there and you just move the targets as need be. So you can see the difference when you do a sweep, whether it's 180 or 360 degrees, and what the arc seconds are compared to a 90-degree sweep. So I don't know about y'all, but that is a lot of zeros before it gives me a number in inches per foot. So it's a very low number inch per inch, and it's a very low number inch per foot. So we're getting very finite on how close we want to get to absolute zero or near zero. When it comes to shaft alignment, we're dealing with offset and angularity. So the offset and angularity, we want to be able to get it as low as we can horizontally, but we have to understand our restrictions when we're dealing with vertical alignment. So when we're dealing with shaft alignment, for vertical alignment, whether it's offset or angularity, the minimum amount of move that we can do is slated by the lowest size of the shim we can use within that system. So right now it's 1,000th of an inch for imperial, and it's 0.01 millimeters for metric as small, and don't quote me on that. I know it's probably 0.005 5 microns, but I still think it's 0.010 for metric. So as you can see here, when you're looking at different technologies and different expectations, the expectations for shaft alignment is going to be a little bit higher from zero than would be triple scan laser, because it's applying a lot more technology and we're able to get to that distance. So hopefully today I taught you a few things about the evolution of precision alignment, and along with a little bit of a timeline, understanding who actually invented the first laser alignment system. We talked about differences in technology, and hopefully I educated you a little bit. So thoughts and takeaways. Are you utilizing the right technology? So you deserve better, affordable, and more accurate systems. So don't just expect the system that you've been using for years to meet that expectation. Go out and look at other applications or other systems to see which one works best for you. There's always a learning curve when you do that, because everybody is comfortable with a certain system, but there may be an easier way to do with the new system. So always keep that in mind. Accuracy and precision at your fingertips with user-friendly software. That's what everybody's trying to get. So always look out and see what's available for you. Hamar Laser has over 55 years of laser alignment knowledge. No one else can truly say they invented the laser. We can. or invented laser alignment. Sorry, not the laser, but laser alignment. We're always innovating and creating new systems to meet customer needs. So one day in the near future, there's going to be a new system that's offered to the market that nobody has. And so when that happens, as we want to move more into predictive maintenance and get away from the standard maintenance protocol, then always look for what's out there, innovating and change to be able to do it. I did add some questions there to be able to, if anybody has any questions. Who is Hamar Laser Instruments? Hopefully I provided that for you. What was the first laser shaft alignment they're known for? That would be the L400. How many patents does Hamar Laser currently hold? Did anybody write that down? So it was 25 current patents and 2 patents pending, so 27 total. What is Hamar Laser known for in today's industry? And we're known for laser alignment. So we do niche markets, and we're breaking out into other markets as well, specific around precision alignment. And then the last question is, who is the only company to have a patented dual beam unidirectional technology? That's 2 beams going in one direction. That would be Hamar Laser. I want to thank everybody for tuning in for this webinar, and hopefully you learned something in this and got a takeaway to be able to look for more information and be able to research a little bit more on what your needs are and be able to identify what system works best for you. All right, Nick, I'm going to turn it back over to you.
Perfect. It is now time for the question and answer session. Everyone, if you have any questions, go ahead and enter them now in the question panel of your GoToWebinar screen and submit them for Terry to answer. Again, your questions will be answered and read anonymously, and if we run out of time and don't make it to the question, Terry will reach out to you directly after the webinar to make sure your questions have been answered. Okay, so the first question we have here, what preparation and execution steps would you suggest to make our alignments faster and achieve our tolerances more efficiently?
So when it comes to a pre-alignment check, it's a pre-alignment check. I mean, a lot of industry is, dare I say it, a dirty industry. There are certain industries that keep an expectation of cleanliness, but when you're dealing with systems down in a basement or underneath other equipment, then that's one of the things we're having to look at, is we're having to look at cleanliness. So making sure that the base is clean, the bolts are clean, making sure you don't have cup washers, making sure that when you do an alignment, when you go back, you're able to physically perform that alignment. A lot of systems want you to do softfoot check within that pre-alignment check. There are companies out there, including Hamar Laser, that does the softfoot check as part of the built-in software within that system. When it comes to getting tolerances faster, the one thing I always say is the pre-alignment rough in. So the pre-alignment check rough in, depending on how big that motor is, that rough in could take you 45 minutes to an hour. I was at a trade show last week speaking to a gentleman, and he said they would give up after an hour, and then they would put the laser on and try to make it work. So when it comes to meeting those tolerances, you want to be able to find a system that can apply speed but also be repeatable and be able to provide that function to be able to do that.
Very good, Terry. This next question asked, who do I reach out to in the mountain empire of Southwest Virginia to speak about Hamar lasers?
Well, you can easily, I don't know if you saw the banner that shows my number and my email, and it'll be provided to you, but you can reach directly out to me. If we do have a distributor in your area, we do have a reseller in the Virginia area, so that reseller is very knowledgeable about the Hamar Laser systems, especially around shaft alignment. So, and that group is learning more and more about geometric to be able to provide customers in that region a lot more answers and be able to get them in the right path.
Sounds great. We have one that comes in here. What about calibration intervals for lasers?
Calibration intervals, geometric lasers range between 2 to 3 years to be recalibrated. If you live in the United States, Canada, Mexico, the Central America, it typically is a 2-week turnaround since the systems are physically going to Danbury, Connecticut. So we're looking at a 2-week turnaround unless there's something horribly wrong. The system was dropped and some some internal components need to be replaced. But for recalibration, for the shaft alignment system, it's every 2 years, goes to Danbury, Connecticut, and we look at it right around a 2-week turnaround to get your system back.
We encourage everyone to keep the questions coming in. I just got one right here. Why do we focus so much on the movable than the stationary during alignment?
Well, normally the stationary can't move. That's why it's the stationary. So let's use an example of a pump. So when a pump is installed onto a base, other things are attached to it before the motor ever connects to it via the shaft and a coupler or a spacer shaft, jack shaft. So whatever that motor is going to connect to with that pump is already installed with piping, electrical if needed, depending on whether it's a thermal pump or what type of media is going through that pump. So there may be insulation in there. So technically, we don't want that stationary to move at all times. We want to be able to use the movable machine, the motor, because the motor is designed to line up to whatever is stationary to make the axis or the power transmission be as close to center as humanly possible. On top of that, so there are times when you have to use the stationary, and I'm going to use a gearbox for example. So if I'm doing an alignment and it asks me during my alignment process to take 5 thousandths or let's say 0.01 millimeters off the front and back feet. So the motor has to go down, but I don't have any shims underneath those feet. So typically what happens is technicians not going to know, if they haven't been trained, what to do in this instance. They're going to go find a grinder and they're going to make that 5 thousandths or that 0.010 millimeter gap to be able to bring that motor down. Hamar Laser offers something called the bolt-bound base-bound option, where it utilizes the feet of the stationary machine, and you can lock certain feet. So I can lock the back feet of both the motor and the stationary machine, this being a gearbox for this example, and I can see if both front feet can be raised to meet that alignment. So there are opportunities where a stationary machine will have to move. But typically when it comes to pumps, we try not to move it unless there's circumstances where we can, and there's definitely circumstances where we can't.
This sounds like a good question right here. How might artificial intelligence or machine learning influence laser alignment systems?
That is a really good question. So right now, artificial intelligence is being looked at to be able to provide you with immediate response to any changes with the system as it goes. Let's talk about thermal growth for an example. So a lot of systems come with the ability to track thermal growth using a geo add-on to that shaft alignment system. So you're able to track that growth or reduction depending on what that system is. So thermal growth compensation either expands or contracts. So artificial intelligence will be able to monitor that a lot better than, say, just a system recording numbers, and be able to provide you a better outcome for tolerance, clearance, what the expectation is for that thermal growth compensation. So when it comes to artificial intelligence, from what I'm seeing, it's in the infant stage. I do have a concern about artificial intelligence, and that is if it doesn't know the answer, it's going to come up with an answer. Whether that's true or not, it's going to come up with an answer. And I can use a prime example of the slides that I just used. I was trying to find dates, and it's hard to find dates on the internet for certain systems. So when I enter in a system, let's say in Chat GPT, to see if AI can provide me that date, it's funny when I enter in a proof technique machine and it says Hamar Laser invented it in 1993, when clearly we did not invent it, but that's what AI could not find a date. So it went to the next thing that it could find. And obviously the last question I asked was, what year was a Hamar Laser system created, just seeing what it provided. So it went off of that. So we still are in the infant stage, I feel, with the AI portion going into shaft alignment or geometry alignment, but it's coming. It'll eventually get to the point where you have somebody talking to you about what your move is. So that's where I'm seeing it go.
All right, this could be our last question right here, unless if anyone else would like to get questions in. What kind of training is required for operators to effectively use precision laser alignment systems?
Well, training is always needed because every alignment system has a different process. I don't care if you used a certain system since 1993 and you're used to that system. If a new system comes in, you may not know the process. So what are you going to apply? You're going to apply the exact same process that you're used to on the old system on the new system, and something's not going to work, whether it's on an iOS, iPad, cell phone, whether it's on a tablet, on your laptop, it's on a handheld, whatever that system is, that system you have to be trained to understand what a basic alignment is compared to any other alignment, like uncoupled, spacer shaft, vertical alignments. So there are different types of alignment philosophies out there. When we come to geo, understanding the geometric requirement. So I'm going to use a prime example. So if I'm laying railroad tracks, how straight do the beams have to be where they interconnect with each other? So understanding that as an operator, I'm able to use a simple straightness tool, whether it's a laser from any company. I can use that laser to give me that straightness outcome of those two beams and that interconnection. Because I'm not worried about the rest of the beam. I just need to make sure that it's flat or straight or level where they interconnect, so I don't have any issues when that train or any of its cars roll over it. So training is always imperative when it comes to any type of laser alignment system, because there is not a laser alignment system that is going to show you everything. Majority of the shaft alignment systems that are out today, they show you how, in quick steps, how to do a basic alignment. So that is literally walking up to a motor and, let's say, a pump. I put on my brackets, I put on my heads, I run the software, I follow this 5, 10, 2-page, whatever that pages are, to do a quick alignment, and I'm able to get through those steps pretty easy. But what happens when it says I need to take 5/1000ths off that front foot of the motor and I don't have shims? That quick start guide or the quick step guide isn't going to help you at that point anymore. Now that's where training is more imperative, because understanding, oh, I have an option to do that, or oh, I can do it this way instead of that way. I can do uncoupled instead of spacer shaft. It'll save me time due to the distance, whatever that process may be. Training will provide that with you or for you.
All right, we got a question in at the last second here. This is a general one, but how tough are Hamar lasers?
How tough are Hamar lasers? So Hamar laser shaft alignment systems have the largest heads in the market. So they're pretty wide. Everybody else has really skinny, tall heads. We have almost like a box that sits there. So how durable is it? We use epoxy instead of glue. Most of our stuff is screwed in. It is plastic frame, just like almost all laser alignment systems. So when you drop something, what are the chances of affecting it? It really depends on how far it dropped, what angle it dropped, where it hit, what's happening. We don't want to be on the 3rd floor of the mezzanine and drop it down 3 floors and expect it to work right when we go down to the very bottom to pick it up. So, what is the durability? They can take a licking and be bounced around. Almost every system comes in a waterproof case that has foam line to be able to protect the system if that case does fall. And I've got a case sitting over here in my office that it fell almost 3 feet. Checked everything inside of it, nothing was damaged. So when you talk about durability in the field, I think Hamar Laser has really durable systems, but I think it's comparable with other systems that are currently on the market as well.
All right, thanks to everyone for their questions. Before we wrap things up for today, did you have anything else that you'd like to add, Terry?
No, I think I said it all. The big thing here was just educating people on laser alignment, what's out there, and opportunities that maybe you haven't considered.
Great. Thank you, Terry, for your time and awesome presentation. And on behalf of the entire team here at Mobius Connect, thank you to our wonderful audience for joining us today. As a quick reminder, the recorded version of this webinar will be made available on CBM Connect, and you will all receive it in an email tomorrow as well. You can see a full list of upcoming webinars and other educational content on CBM Connect, which you can visit directly at cbmconnect.com. If you're interested in engaging with other industry professionals or you would like to participate on the industry's live feed and ongoing forum discussions, you can do so by visiting Mobius Connect at mobiusconnect.com, and you can follow us on social media at Mobius Connect to stay up to date with the latest community happenings. Thanks again for joining us. Have a great day. Please stay safe, and we will see you next time.